enthalpies of reaction, enthalpies of combustion, or enthalpies of formation from other data. We get this information from experimental results done under standard conditions. Now, what we often find is that most reactions don't happen under standard conditions, they happen under normal, everyday conditions. So what I've got here is a reaction that hasn't been done under standard conditions, so I wouldn't expect to get the value for this reaction that I find in a book or online. Okay, I expect to get a different value. But what I want to do is go through with you how we use experimental information to work out the enthalpy change of a reaction, or delta RH. You'll notice the little circle is not there because this is not under standard conditions. Additionally, we would get a number that is wrong, and in an exam question we'd have to explain why this number would be wrong. If it's done in a beaker, which is this diagram is meant to represent, energy transfer with the environment is going to affect our result. It will affect the change in temperature. Okay, so in this experiment I've taken 1.31 grams of zinc powder and I've put it into exactly 100 mils of 2 moles per litre copper sulfate. The concentration of the copper sulfate in this example is not important. It is excess copper sulfate. You won't even notice a colour change if you do this one. You notice that the zinc turns a pinky browny colour as it turns into copper, but actually you don't notice any change to the solution. So what we do is we have a thermometer in there before we add the zinc and we find that it is 22.5 degrees. After adding the zinc we notice that it goes up to 30.4 degrees. So something has changed, specifically the temperature. If the temperature has changed, it means there must have been a change in enthalpy as well. So how do we translate that information into something meaningful, which is energy, given the symbol Q? Well, I need some information. First of all, I need to know what each of these things actually mean, and we're not given this equation in our exams, by the way. You need to know this one off by heart, as well as the other equations that I'm going to put up on the board today. So this you need to know off by heart and what it means. So this Q is going to be in joules. Okay, Q is going to be in joules, not kilojoules. So just keep that in mind. Okay, it's energy change and it's in joules. M is the mass of the thing that changed temperature. Mass is the thing that changed temperature. M is the mass of that thing. So in this case, it's our copper sulfate solution. Because we never found the initial temperature of the zinc, did we? So we don't know what its temperature was. So in this case, it's the mass of the copper sulfate. Here's one thing you need to know. 1 mil, we assume, this is not always true, so it's one of those assumptions we might discuss in an exam question. We are assuming that 1 mil has a mass of 1 gram. Okay, 1 decimeter or 1 milliliter, same thing, is 1 gram, so that's an assumption. Okay, it's often wrong. Okay, in this case it probably is slightly wrong, but it's close enough for what we're trying to do. C is sometimes called S as well for specific heat capacity, but in this case this links to the assumption that we've made. C is the specific heat capacity of water. So it's the same thing all the time. It's 4.18 joules per gram, hence why we need the mass, per degree Celsius, which is what T is clearly going to measure. Okay, this will be given to you. They will give you the number to use, either 4.18 or 4.2. I would suggest they will usually give you 4.18 so that your final answer can be to 3 significant figures. And the last thing is delta T. It's not just T, it's delta T, which is our temperature change, hence why Q is an energy change. And the one thing I will say to you here is it doesn't matter if it's positive or negative, it actually doesn't matter. However, we will do it, and that is in degrees Celsius. Okay, so we need to get that information from what I've got here. So the first one's an easy one. I have asked you guys to have your calculators handy to help me with it though. The first thing I need to get is my temperature change. I'm going to go from right to left actually, backwards, to get to my Q. So my temperature change is taking the bigger value and subtracting the smaller value, or if you want to be more precise, the final temperature minus the initial. So 30.4 minus 22.5 degrees Celsius. 7.9. Okay, so we've got one of those values we can plug into our equation there. C is already given, 4.18, so I now need the mass. Now there is an assumption made there, but the first thing I want to check is, what thing do we know the change in temperature of? The solution or the solid? Which one do we know the temperature change of? The solution. It says it's 100 mils, so using our assumption, how many grams is that? 100 grams, okay? So we actually already know this to be 100 grams. I'm not going to put the point O because it's an assumption, so I expect it's not 100% correct. So now I can plug those numbers in. This is what I need you to do for me, please. Q equals 100 times 4.18 times 7.9. So if I can have a Q value, please. 3,302. Oh, excellent. Okay, so rounded off to two significant figures here, but actually most things in there are 3. That data, raw data, is 3, so we can stick with that. 3,300 joules would be the rounded off value, which becomes 3.3 kilojoules. I've converted it into kilojoules because this is important for calculating enthalpy change. Enthalpy change is Q over N. Now be careful, you need to know whether it's exothermic or endothermic to know whether this value has to be positive or negative, so you need to make that change. The way I like to think of it is if the water got hotter, then it must be an exothermic reaction. So if I take the negative value for Q, then that equation actually does the sign for me straight away. Because I know it's getting hotter, Q is a positive number because it was a positive temperature change, but I need this one to be negative. Now the reason for that is to do with conservation of energy. What is this the Q value for? What is this the energy change for? Which substance? Zinc or copper sulfate?
Copper sulfate.
Copper sulfate. But actually what we've got is the displacement of zinc occurring. That's what this reaction is. So we actually need to know what it is for the zinc. So we're actually going to be looking at the amount of zinc. If this value goes up, then the value for the zinc must go down by the same amount. Conservation of energy. Can't be created or destroyed. It's being transferred effectively from being in the zinc to being in the copper sulfate solution. So if this number got bigger, for the zinc it must have got smaller, which is why I put the negative symbol there. So we've got that number, but we haven't got this. How do I find amount? I'm hoping this fits on the screen there. N equals what? What relationship with the things you've got there? There's 2 possibilities, C times V, but that would be for the copper sulfate. What else could you use it for? I've got something precisely weighed out. How do I find it for a solid? Good, so little m over big M. Okay, and big M can be atomic mass as well. In this case it will be. So in this case it's 1.31, need you guys to be my calculators again please, over 65.4, which is the atomic mass of zinc. There's only one zinc in zinc, so we do that number there. Some helpers there to 3 significant figures, please. .31 over 65.4.
0.02.
3 significant figures, so 2 more numbers. 0.02. 00. Great. Sorry, I'm being that precise for a reason. Okay, so we need to know precisely how much. So 0.0200 moles. Right, now I can use that number in here, that number in here. So my delta H, let's change colours on that one. And if we go with that, what do we get? Negative, hopefully. So negative 3.3 over 0.02.
Negative 165 kilojoules.
Kilojoules per mole. Awesome. So we now have our value from an experiment. So you need to get your head around the fact there's two things happening. One, there is a solution getting hotter or colder. That will give you a value for Q. That, therefore, is the change in energy. The negative of that is the change in energy of the other substance, which you'll most likely have weighed out precisely. That will allow you to find the enthalpy change. All right? So that's your process. You've got to look at both chemicals and treat them independently, but the energy change for one, if it's up, is equal to the energy change for the other one in the opposite direction. Okay?